Hello, my name is Mark Burton from Albuquerque, New Mexico. I retired from the Air Force in 1999, and I've been teaching high school science, technology, engineering, and math for 20 years. I recently transitioned to tutoring. I tutor online and local students, and many of my students have requested tutoring in MATLAB. So I offered them the opportunity to transition the code from MATLAB to Scilab and learning the Scilab commands. I have noticed that the MATLAB is used almost exclusively in assignments. So this particular presentation applies to textbooks, it applies to teachers that make assignments, it applies to educators who might have the opportunity to use Scilab instead of MATLAB, and also to politicians who have the authority to select textbooks that could include Scilab instead of MATLAB or as a particular option. As a tutor with over 1,000 hours, I am seeing a lot of requests from students that need either training in MATLAB or a transition to something less expensive. This particular presentation focuses on 3 examples that I use for Scilab. There are obviously many more. The second example on this presentation comes from a book on orbital mechanics that has 50 MATLAB programs in the back of the book. The third one, book on probability, has a section at the end of each of 12 chapters on MATLAB. So there are a lot of opportunities for translation from MATLAB to Scilab. First of all, there has to be an understanding of the topic itself. So any teacher in these STEM subjects would have the ability to understand the problem, and with a little bit of extra work to understand the actual coding in Scilab. So let me get into the first area on the numerical method for evaluating an ordinary differential equation. So just to introduce the problem, the ordinary differential equation is y prime is a function of time and y of t. So the method for solving that ordinary differential equation, it comes from this equation, a step function, subscript of y, n plus 1, n, and n minus 1. To code this, the subscripts are shifted 1 space to eliminate the a priori -1. The second method uses a subscript of n plus 1, n minus 1, n minus 1, and n minus 2. So this one is shifted 2 places to get rid of the negative subscripts. The r in this first line is used to give some sample points throughout the plot, and the exponent is a function of pi, imaginary numbers, and a linspace generation. This is a MATLAB code, but the linspace is also used in Scilab. So these next 2 commands, this is in MATLAB right here, and I will be showing the translation of that to Scilab in the next slides. So the first one plots the dark line, the second one plots the dotted line, and a couple of these commands are not needed in Scilab, and the last one is a sample point that is placed in the loop of this dotted line to determine whether it's stable or not. This particular point is evaluated according to this last code for 3 different roots inside the dotted line, and we'll see why or why not that is stable. So the commands in Scilab, I'll just go through a few of them. First of all, the Scilab uses the percent sign in front of pi, percent sign in front of I, the imaginary number. When I created the complex vector, I had to replace those variables with the percent sign, and usually adding multipliers and exponents that may not be implicitly understood in MATLAB. And then, this is the main difference in MATLAB Scilab, I'm not able to directly plot an imaginary function in Scilab. That has to be broken apart into two different plots, or two different commands for the plot. So it was separated into real and imaginary components. So you'll see in the code how that affects the plot. When I originally plotted it, I did not get the plot that was given to the student for the assignment because the Scilab program did not recognize an imaginary function. So these are the two functions I used for plotting the solid line and the one used for plotting the dotted line in the linear multi-step method. So let's take a look at how those commands were derived. This is the point that was randomly selected, point 2 real and point 8i on the imaginary plot. So this is the actual Scilab plot that, if you remember the MATLAB plot, is very close to that. It's just extended a little bit for the horizontal axis. So this test point, it falls within the lobe of the second method, and we'll look at why or why not that is stable. So this is understanding the method used. Doesn't have anything to do with the coding, but to understand how to code effectively, the method needs to be well understood. So this is a general method for linear multi-step method. Notice that the exponents match the subscripts of the previous functions. So these exponents, once the function is shifted to get rid of the negative subscripts, then this can be directly coded into what I used for doing the plot in Scilab. So here's our R vector, R minus 1, 3 times R minus 1 over 2. And then for the second one, this was shifted twice to get positive exponents and mapped to this exact function. Okay, a look at stability of the solution to an ordinary differential equation, whether it converges or diverges. Stability is related to where it is on the plot. The graph that was given to the student showed the MATLAB plot, and I showed a Scilab plot. Now see if we can go back to that. Here's the Scilab plot. Any graphs to the left of the 0, here's the 0 on the real axis, this is considered stable. Notice the second method is the dotted line. All of that is to the right of the 0, so it would be considered unstable. This particular method shows up in literature. This one was just proposed for the assignment given to the student to show the difference between an unstable and a stable solution set. let's go back to, this is the stable, solid black line, unstable red dotted line for those reasons, and then this randomly chosen point on the dotted figure has roots, and that was what was generated by the MATLAB code. There were 3 roots given, and the requirement for stability is at least one root with magnitude exactly equal to 1. And none of those roots fit that criteria, so that's another indication that that dotted plot was unstable. This was another example I just added because while I was doing this presentation, I received a request from a student. It had MATLAB code, so I looked at the way to change that coding into Scilab, and it was fairly simple. These are just 4 simultaneous equations. I put that in matrix form, ax equals b, and then I used the Scilab coding for solving those equations and came up with all the variables that were included in that problem. Most of the time in a problem like this for electronics, there's only 1 or 2 variables that are requested, but this is the nice thing about using a matrix solution, and it's very quick in Scilab, just as it is in MATLAB. But if students don't know how to use either matrix calculators or Scilab, then they would have to do a lot of this by hand, or they don't get all the information available from the matrix solution. Okay, the second exercise as an example of a MATLAB to Scilab code was orbital mechanics, and this is an algorithm given in the book by Howard Curtis called Orbital Mechanics. And that book has 50 MATLAB scripts at the end of the book that I'm working on converting to Scilab. This first algorithm is applied to a mechanical system with a mass, a damper, and a spring. So this particular example shows the differential equation written for that system. So this is the derivation of this. These are 4 equations written on that system and then solved for position. So that position obviously is an extremely complex function as an exact solution to these differential equations. So the purpose of this first exercise is to show numerical method solutions for that differential equation and compare it to the exact solution. So this is the exact solution. As you can see here, this is the same equation as on the previous slide. And then the rest of the exercise is using MATLAB code, converting it to Scilab code, and plotting various functions using Runge-Kutta, method 1, method 2, method 3, and method 4. So for numerical solutions, the code is given in the back of the book using a Runge-Kutta method, quickly translated to Scilab, and we get various plots. So this particular slide shows some of the differences in the code and the syntax of Scilab. Select is the Scilab equivalent of switch. There is a function that is used to generate some of the derivatives, first and second time derivatives, and then for output, this plots the solutions. It plots an exact solution, the first, second, third, and fourth methods of Runge-Kutta. So there's 3 sections in the MATLAB, which I combined into one program as I'm going through understanding the program, rewriting the program, and generating the Scilab code. I'm putting these together. This has the flexibility for additional inputs. That's why it's in 3 different subsections. So here's the output, shows the actual solution, the exact solution, and the Runge-Kutta 1, 2, 3, and 4 methods. As you can see, the difference is getting much, much smaller by the time we get to the 4th method and using a smaller step in the method. Okay, last example is probability. These were fairly straightforward examples. Three examples in the book in chapter 1 was to generate 4 random numbers and then test to see if they were less than 0.5 using the random and sum functions to perform 75 experiments, using a ceiling, random, and history command to simulate the testing of 100 microprocessors. These are a couple of the differences in the transition from MATLAB to Scilab. One, MATLAB says to use histogram and Scilab uses history. MATLAB histogram correlates to the Scilab hist plot. So those were a couple of changes. So as students, if they start using Scilab, they'll have a general understanding of the commands needed for Scilab, and they'll have a very good correlation between the MATLAB and the Scilab coding. This chart shows the cost for MATLAB. Obviously, Scilab would be 0 cost, just requesting donations. This is an annual fee for standard MATLAB program education, and even a student is charged $100 a year to use MATLAB. Also to note that when you get a student version of MATLAB, you don't get all the add-ons. It comes with 10 add-ons, and you have to buy each additional add-on for $30 each. So that's another reason for using Scilab, the hidden costs of additional add-ons. In conclusion, this was a report from Forbes in 2018. Student debt was $1.52 trillion in the United States, and that 44.2 million people owe debt on their college education. Part of this is fees, part of it is mandatory. When you pay the fees in a class, you have to pay fees to even do your homework online, which would include programs like MATLAB. So it's almost a conspiracy to make students pay for something that they could get free through Scilab. Scilab is growing in capability, just like Linux has grown in the past 10-20 years. Scilab is growing along with MATLAB and adding a lot of different features that match or exceed the MATLAB capability. So I think we can work together as a community to inform and educate students, teachers, administrators, authors, and politicians. The authors that write the books, if they know about Scilab, they may be more inclined to use it as examples or alongside with MATLAB code. And I think as students graduate and have an ability to use Scilab in industry, the industry won't rely as much on MATLAB, but could also venture into using Scilab as a resource for projects. I'm a retired Air Force. I did projects in California on ICBM launches, projects in Ohio on ground launch cruise missile launches, and also projects in Albuquerque on nuclear surety on ICBMs. So a lot of those involved coding. My last job was involved in the software safety. I wrote a paper and also a requirement for contractors to examine the safety of software in the area of ICBMs. I want to thank you for this opportunity to talk about the transition from MATLAB to Scilab. I hope to participate further in the future, and if possible, attend a future conference. Thank you.